Hi everyone. In this recording, we will talk about our presentation, which is Missing Concept Recommendation System. These are the outlines of our presentation. We will start by the motivation and then give general overview about our recommendation system. We'll talk about the related work, the problem definition, and then we will propose our method. We will talk also about our challenges and the concept graph that we have built. We will give some empirical examples and finally the evaluation. So the motivation, imagine that one student wants to learn about parameter estimation. So he will use Google and will write this query to find some articles. Assume that he found these two articles. The first one just give a very short overview or introduction about the topic, while the second one is a Wikipedia article that explains the topic in details. As you know, Wikipedia article contains many hyperlinks. So for the student to be able to understand the article, he needs to understand the concept of those hyperlinks. So if the student doesn't understand any of them, he needs to click on those hyperlink to open another Wikipedia article which has other hyperlinks, and if the student doesn't understand those hyperlinks, he will open another Wikipedia article and so on. So as the result, the student either get lost or he will consume a lot of time trying to understand the topic. So to solve this problem, we propose missing concept recommendation system. The basic idea is that we want to bridge the gap between what the student wants to know and his background of knowledge. So the main goal is that we want to recommend the minimum number of concepts needed to understand the concept, because we want the student to understand the concept in a short period of time and easily. So the general overview is that our recommendation system is a combination between search engine and recommendation system. So we will ask the user to give two types of query. The first one is the target query, which is the topic he wants to learn, and the second one is the background query, which is the concept he already know about the topic. So based on these two inputs, we want to recommend a subgraph that bridge the gap between the target concept and the background concepts. The question is that how can the system recommend those missing concepts given those inputs? We will assume first that this concept graph is given, but we need to ask how concepts are related in that graph. What are the relationship between those concepts? So to answer this question, we try to examine those hyperlinks, and we found that the concept of those hyperlinks belong to one of three categories. The first one is important concept, which are like a prerequisite or the subpart. So for the student to be able to understand the main concept, he needs to understand all of them. So in that case, we call them depend on and. The second category is concept of different methods. So for example, to understand parameter estimation, you can learn maximum likelihood estimation, or you can learn maximum a posterior. So it is sufficient to understand only one concept. So that we call them depend on or. So you can learn one of them to get knowledge about the topic. The third category is unrelated concepts. So the student doesn't need to understand any of them. They have no relation with the main concept. The general overview is that given two random variables, the first one the target query and the second one background query, and also we have the concept graph, which is directed and weighted graph that has two types of edges. The first one depend on and the second one depend on or. Given those inputs, we want to accomplish three tasks. The first one, map the target query to one target node. The first task basically is map the target query to target node and background query to one or more background nodes. And then we want to find the subgraph that bridge the gap between nodes. And finally, we want to recommend the document that explains those concepts. In this project, we will focus on task 1, which is find the subgraph that bridge the gap between the target node and the background nodes. So before go further, we need to mention some of the related work. Uh, to the best of our knowledge, there is no work address this problem and recommend concept to students. However, there are some work on building the concept graph. Basically, they link the concept to knowledge base such as Wikipedia, and then they use supervised methods to relate the concept based on their dependency. The main challenge they face is that how they get the training data. Basically, they either use crowd to get the training data, or they label the data manually by asking some expert to help them. The problem definition here, as we said before, we have the graph, which is directed and weighted graph that has two types of edges, depend on and depend on or, and we have a set of background nodes, and we have only one target node, and each node assumed to be known or unknown, or the node will be unknown at the beginning, and if the student give us background node, all those background node will be updated to known, and all the nodes that this background node depend on will also be known nodes. What we want to find is that we want to find the subgraph R that has a set of recommended node we want to recommend to the student. But the question is that how we can find the optimal R? What are the best subgraph that explain the target concept given those background concepts? So the proposed method is that if the concept has a depend on and relation with other concept, so we think that it is important to include all those concepts in the subgraph. But if the concept has a relation of type depend on or with other concepts, I think it is sufficient to learn one of them to help the student get knowledge about the topic in a short period of time. And our assumption is that the optimal R is the one with minimum number of nodes and minimum depth. So we think that the optimal subgraph is the one that has minimum nodes, so the one that has minimum concept, and also the one that has minimum depth or minimum diameter. So in this case, we decrease the dependency between concepts. So it will be easy for the student to learn the concept in a short period of time. Now my friend Shadi will complete the presentation.
So our proposed method consists of 3 different steps. First of all, we prune all in-links to the target node, and we prune all the outlinks from the background node, as shown in the picture below. And then we calculate the score of each subgraph, and finally we recommend the subgraph with the highest score, if possible. So to choose the subgraph with the highest score, our scoring function is built upon the work by White and Smith, who calculated the relative importance between two nodes. In this work, the depth of the graph is taken into consideration. However, in addition to that, we also take the number of the nodes of the subgraph in our algorithm. As mentioned before, to get the subgraph with the lowest number of the nodes and shortest depth as the optimal solution. Before finalizing our scoring function, we examine different scoring functions as shown here. The first one, which is the most trivial one, panelize both the number of the nodes and the depth of the graph. However, as shown in the example, it gives the same score for the subgraph. For example, if we have the node number as 200 and the path as 3, and also we have for the other subgraph the node number as 3 and the diameter or the path as 200, these two would have the same score. Our scoring function take this and correct the scoring function. It panelizes both the number of the nodes and the diameter. If the same diameter exists for both of the subgraph, it prefers the subgraph with the lower number of the node. If the same number of the nodes exist, it preferred the lower diameter and retrieved the subgraph with the lower diameter, as mentioned. Throughout this project, we had some challenges. The first one is creating the subgraph, creating the concept graph. As mentioned in the background work, there are two types of creation of the subgraph. One of them is manually building this, which takes time and it needs annotation. The second one is automatically creating the subgraph, which is hard, error-prone, and needs extensive evaluation again at the end. We created the concept graph for this study manually by using the course on Coursera, text retrieval and search engines taught by Professor Jai. Our total number of the nodes are 164 and our total number of the edges are 192. The other problem or challenge was finding the optimal path. In addition to different scoring functions that we had to examine, we also yet want to know or are trying to study if our hypothesis, which the smallest subgraph always guarantee the best subgraph, is correct or not. Also, it would be good if we could find the degree of dependency between the nodes and graphs. But it is hard to estimate, and it needs experts to help us with coming up with that dependency degree. And finally, from the user's perspective, it's hard to choose sometimes the background query because the user does not know how to connect the background that he has with the target that he wants to study. We will work on this in the future using different sources to build this knowledge, such as course studied in MOOCs. In this work that we presented here, we give this option to the user to give no background node and just provide the target node that is desired for learning. Sorry. So this is the concept graph that we built. As mentioned, it has different number of nodes and edges, and it is on the concepts and prerequisites that we have on Coursera text retrieval system. So this is one of the empirical examples that we have. So the first empirical example that we have here, the user provided the target query as vector space model, and the user also provided two background queries as TF-ID evading and document length normalization. This is the subgraph that connects the background query and the target query that the user provided. This is not yet the optimal solution that we will recommend.
So we will recommend this solution because it is bridge the gap between the target query and the background query. And you can notice from the graph that the student asked for a vector space model. And one of the concepts that vector space model depends on is the state-of-the-art vector space model ranking function. And in this subgraph, we recommend the BM25 Okapi as the state-of-the-art ranking function because because it's easy to understand this, because you need to understand it to understand the TF transformation. So to understand the TF transformation, you need to understand the BM25 transformation, which depend on the BM25 Okapi. But the state-of-the-art vector space model ranking function also include pivoted length normalization vector space model, which will not be included.
In this subgraph, as we can see, we have the shorter path, and also we have less number of the nodes. This subgraph is what we recommend to the user, regardless of the queries that background query that the user provided, because we think this is the optimal solution, and the user can learn the vector space model in the shorter period of time because of the less number of the concepts in this subgraph.
And we can notice here for the state-of-the-art vector space model ranking function, we recommend the pivoted length normalization vector space model because there's no relation with other concept in the graph like previous one.
In our second example here, the user did not provide any background query, we have the target query as evaluation of text retrieval systems. As you can see, this is a denser graph compared to the previous one, but because we do not have any background query, this is the optimal solution based on the target query that the user provided. So we still are working on the evaluation part. For the evaluation part, we'll use user study with experts and students who studied this concept, the text retrieval systems. We'll test our hypothesis by using different scoring functions that explore the effect of more nodes and also explore the effect of higher depth. We provide these subgraphs that are generated using different scoring function to the expert and students and ask them to choose the one that is the best solution and compare that with our provided or retrieved subgraph from the algorithm that we just talked about. We hope to finish that for the final report, and we also provided some references here. Thank you so much for listening to us. We'll be happy to answer your questions. You can post on Piazza. Thank you so much.